Professor, did the lecture start? It's not showing on the YouTube link. Okay, that's fine.
Hi and welcome everybody to the lecture titled Visible Light Communication. This is a lecture which is part of a series of lessons on 5G technologies. So in today's lecture we will be talking and discussing about visible light communication, which is an optical wireless communication technology termed and named LiFi, light fidelity. So basically we are going to be covering the applications that this technology can be used for, the white LED structure, the illuminance distribution, the channel models, and the challenges alongside the solutions. So beside that, we'll discuss the transmitter structure, receiver structure of optical wireless system, and identify the key differences between RF conventional transceiver structure and optical transceiver structure and see the advantages, merits, demerits, and differences between them. So, as you may remember from the previous lecture, we talked about millimeter wave communication, and we showed you that the main problem that pushed us to go to upper and higher frequencies is the fact that the demand on the data rate is increasing exponentially. The internet traffic, the data demand coming from video application, real-time gaming, and many applications like Instagram, TikTok, Facebook, YouTube, Twitter, many of these social platforms and other now becoming like video content, and video is consuming lots of data, and this data day by day users are generating extremely massive amount of data, and with the current technology we cannot suffice or meet the requirements of this demand. So that's why we are pushed to look for alternative solutions that can meet this huge demand. One of the solutions we talked about in the previous lecture was the millimeter wave communication systems. In millimeter wave, we said it's different than the normal conventional microwave system in the sense that we are using higher frequencies at gigahertz frequency spectrum in order to be able to serve more users with high demanding data rate applications. So now this is another technology that's trying to solve this issue, but kind of competitive to millimeter wave communication. Here we are talking about nanometer wave communication. You understand me? Why did we name millimeter wave communication this name? Why did we give this name? Because the frequency we operate over it at that band is around in gigahertz, like 30, 40, 60 gigahertz, and so on and so forth. In visible light communication, which is operating in the visible light region, and if you look at the lambda length, you will notice that it ranges between 400 nanometer and 700 nanometer. And this, if you translate this to frequency, it becomes in terahertz. So we are now talking about terahertz communication or nanometer wave communication, which is completely different than gigahertz communication or millimeter wave communication. And we are in the tera region here. So what are the key and different features that you will have when you move to such spectrum? And what are the implications on our practical life when you consider the spectrum? We all know that visible light communication is used only for lighting, yes, for luminance. You are using lamp in your room to give you light so that you can see things, and basically you are using it for one single functionality, which is lighting. But now someone is coming and saying, no, you can use it also for wireless communication, for sending data and for serving users with who are demanding massive amount of data. So this is very new, and this is very amazing and beautiful thing to have, because now for in one thing, one product, you are using it for two functionalities simultaneously. You now you can think of using the light bulb you have in your home for not only lighting your home or your room, but also for sending data internet connection to you. And this is, I mean, this is something different than RF. Everybody at home he has his Wi-Fi access point and using it for internet connection. But now I'm coming and telling you you can use your light bulb for as an access point to give you internet and simultaneously light your home. That's pretty amazing and different totally than the previous generations. So but how does this work? How does this function? And how is it really practical to use it? So now that's why in this lecture we are dedicating it to this topic, and we will disclose all this information and the related things that are mainly concerned about the transceiver structure in terms of transmitter, receiver, and the channel model and the differences. So visible light communication can be used for vehicle-to-vehicle communication networking in indoor environments, and it has been used for a long since ancient time, 1880s. They were inventing the photophone, but it was not really practical. Yes, they were able to invent something that can use the light for communication, but it was with bulky devices, and that's why it was impractical to be used. But with the current advances in technology, visible light communication can make use of the optical components in order to make compact and efficient devices that can use optical wireless communication for transmitting and receiving data. So indoor visible light communication, you can use it in home, in offices, in shopping centers, plane, hospital, convention centers. All these mainly are indoor environments where you can use your visible light communication and serve the users with huge amount of data. I'm not talking about a few megabytes. You are talking about gigabytes communication links, and this is what we are experiencing nowadays. Yes, with the coronavirus pandemic, we are always suffering from the lack of the infrastructure, a very powerful infrastructure to serve the huge demand nowadays on video communication, synchronous and asynchronous. So for having extremely high quality video that can go forth and back with very low short delay, you need to have very reliable high speed communication networks. And visible light communication is one of the candidate technologies that can serve such a goal. So the advantages of visible light communication can be summarized in the following points. First, it's very safe for health. And why is that? Because light is always around us, yes? We are always exposed to sunlight, we are exposed to industrial light, artificial light inside our homes, schools, and buildings, offices here and there. And it's basically the light, the frequency of the light is so high that it cannot penetrate your room, the walls of the room. It's just confined within the area that you are located in. So your signal cannot go outside of the room you are working in. And if your signal cannot go outside of the room you are working in, then this means that your communication is secure, because your signal cannot penetrate the walls. And if it cannot penetrate the walls, this means nobody can come from a remote distance and listen to my communication and try to hack it and decrypt it. So it's safe and secure. What's the other advantage? There is no interference like on RF signals. You know, RF signals are operating on 1 giga, 2 giga, 60 gigahertz communication. You are operating on terahertz. The band is very far from the band allocated for RF spectrum, and that's why you don't cause any interference. Plus, the interference in visible light communication is less than the interference in RF signals. Why? Because your signal, when you use a light bulb like an access point, and this light does not penetrate the wall, does not go to the next room adjacent to your room. In this case, your data, your signal is only within your room. This means that it doesn't cause interference. Not only it's secure, it cannot go to the other room, but also it doesn't cause interference to the other light bulb that uses the same spectrum in the next adjacent room. And therefore, if you reduce the interference, you increase the efficiency of your system, and the speed of your internet will become extremely high, and because of increasing the efficiency due to reducing the interference. And as I said before, it's confined to small geographical area. However, now, as we know, each and every single amazingly beautiful technology that we come up with, it has obviously some advantages, but on the other hand, there are some challenges which are basically coming due to the disadvantages coming along with this technology. These challenges form the research direction of the community who are working on this technology. And as we said before, we have to like challenges, because challenges means there are problems that if you fix, you can bring something valuable to the people, and people will buy, will use, and economy will thrive accordingly. So what are these challenges? One of the challenges is the connectivity while moving. In RF signals, when you use normal cellular wireless signal like 3G, 4G, the RF signal is propagating for like, let's say 5-10 kilometer, and this can cover large geographical area, huge geographical area, and your signal can penetrate through walls, so you don't need line of sight communication. And if you are, first of all, you can move around while you are still being connected to the base station. Second, if you move from one point to another, there is a very mature technology that can handle this process via something called handover. But what about invisible light communication in LiFi? Can you handle this? Can you take care of this thing while you are not losing the connection with the main access point? This needs to be rethought, and think about it one more time. So connectivity is very important while you are moving in visible light communication, and you need to address this challenge. Plus, we have the multi-user support issue. If you have multiple users and you have one access, how are they gonna communicate with the base station? The second issue is dimming. Let's say I want to sleep and I want to reduce the light. Does this affect the data rate? do we have any relationship between the light intensity, the light value level, and the amount of data rate you can communicate? So we need to know this relationship and know how to handle this. And then the shadowing issue. If something blocks the connection between you and the base station, the line of sight, can you still get the data from the reflection coming from the door or the wall or some other objects inside your room? And can you extend it to large geographical areas, not only to small geographical areas? So these are the challenges, plus the interference, plus the modulation. How are you gonna do the modulation? And some other things. Now for indoor visible light communication, we mainly use light emitting diodes, are preferred sources for dual purpose of lighting and data communication. And basically because of the following features in them. First, eye safety regulations compared to laser, longevity, lower cost, and mercury free, less consumption, high speed, have a smaller and compact size compared to the large antennas used in RF and some other devices as well. And it has minimum heat generation plus higher tolerance to humidity and a much higher energy conversion efficiency. White LEDs with luminance efficiency greater than 200 luminance per watt are now available in the market. That's very big advantage to utilize these lamps for not only lighting but also for communication. What are the rival technology for LiFi? Obviously Wi-Fi is one of the rival and competing technology with LiFi. And because but like Wi-Fi, we know all that Wi-Fi is not very reliable connection because of the interference that happens on that band. It's very congested and it's not regulated and unlicensed. So basically you need to configure it in a very proper manner so that you can make the most use out of it. And you cannot increase the capacity easily because you are limited in the spectrum. Mainly you can get maximum, like in Wi-Fi N 802.11n, you can get up to 300 megahertz. So if you are 1-2 users, it's okay, very good, very nice. But if you are more than 100 users and you are using all video, like these days, then you will suffer some delay and some low quality communication. That's why the scalability is very limited and the efficiency is not that high at Wi-Fi. To do that, sometimes we have to use high order modulation to increase the data rate, but when you use high order modulation, you reduce your range and your reliability becomes lower because there is a trade-off between data rate and reliability, and especially when you go to higher order modulation. And Wi-Fi is used in office building, which is a conference centers, stadiums, and mainly it can be used in indoor and outdoor, but mainly in indoor. And this is where LiFi, visible light communication, is supposed to be used in indoor communication. But LiFi, on the other hand, has lots of spectrum, and this spectrum enables having a communication link that can provide you 10 gigabit per second, which is pretty amazing and can serve hundreds of users with the required data rate. What's the other rival technology? Bluetooth. But Bluetooth not extremely very rival because the bandwidth is even much smaller than the bandwidth of Wi-Fi. Plus the range is short, very short. But there are some new rivals like millimeter wave communication and ultra wideband. The most recent one is millimeter wave communication, where you have your communication at 60 gigahertz, and you can also provide up to 10 gigabit per second sometimes based on the conditions. And one of the standardized technology in the market that uses gigahertz communication, millimeter wave, is WiGig. So now let's have a look about the key differences between visible light communication, infrared, and radio frequency in terms of bandwidth, distance, security, services, noise, power, mobility, and coverage. Starting with the bandwidth. So in visible light communication, the bandwidth is really very huge, very massive. Like you are starting from 400 nanometer to 700 nanometer. 400 nanometer is near the red color, and 700 nanometer is near the purple color. While in infrared is also you have from 800 to 1600 nanometer. In RF you have regulated and limited. What do I mean by regulated? You need to license it from the government to use it, and it's very expensive. I told you, very expensive. It costs you million, even billion of dollars to license a spectrum there and use it for communication. Electromagnetic interference, in visible light communication, you don't have any interference coming from electromagnetic. In infrared also you don't have, while in RF you have lots of interference coming from all the electronic devices and all the other operating access points in the environment. So line of sight, visible light communication requires line of sight. Although you can get some data from the reflections, but it will be weak somehow, and it's not very reliable. So infrared and visible light communication, they require line of sight communication, while RF does not require line of sight. Distance is very short in VLC and even shorter in infrared, but while it's the distance is really not that short in RF. It's very long. You can communicate over 10 kilometer or even more sometimes. What about the security? In visible light communication and infrared, the security is amazing. Like you have, because why the security is amazing? Because your signal is confined inside your room. While in RF is poor because your signal is propagated through the air in an omnidirectional manner to all the directions. So any malicious attacker can set a receiver and start tabbing your communication and recording your signal, and then take it to the lab, process it, try to decrypt it, and get your message. Now the standards, regarding the standards, visible light communication already have a standard, and this standard is called IEEE 802.15.7. This number is the standard of visible light communication, transceiver structure, physical layer and MAC layer. While in IRF, well developed long time ago, it's already being used in the market. RF is very mature. There are many standards related to RF. What about the services? Visible light communication provides illumination plus communication, while infrared provides only communication and sometimes some other like you cannot use it for illumination, the infrared, although it produces a light, but that light is really so little that it just kind of a pointer. You can use it as a pointer, but you cannot use it for lighting purposes. And RF, you cannot use it for lighting purposes, of course. You can only use it for communication and sensing or some other purposes, but not for illumination. What about the noise sources? Noise sources in visible light communication, the main source of noise is sun. Sun, because sun is basically generating the sunlight is in the same band as the light of the bulb. You are in the visible light region, yes? So the sun causes interference to your communication. That's why we don't use visible light communication outdoor, because outdoor, especially during the day, you have the sun power is much larger than the LED power, and that's why your communication won't be very effective as is the case when you deploy and use your LED indoor. So the same with IR, infrared, you have sunlight and other ambient lights. And RF, all the noise is coming from all electrical electronic appliances and some other operating access points in the regions. Now, these are the differences in terms of noise, and in terms of power consumption, visible light communication is low to some extent, and also infrared is low because it's short range communication. You don't have lots of power to reach large distances, while in RF it's very medium. Like the power depends on the range you want to communicate to. Yes, if you want to reach 10 kilometer, you need to increase the power. The mobility in visible light communication is limited. In IR is even more limited. In RF is not that limiting factor. In RF, it's, as I told you, one cell can cover, one base station, one access point can cover an area of more than 10 kilometer range. Sometimes 50 it can reach. But like within 10 kilometer you can cover a town. So you can easily move around from one point to another while being connected with the access point. You don't lose your communication. The coverage in visible light communication is narrow and wide. In infrared also narrow and wide. While in RF mostly wide. So these are basically the key and main differences between visible light communication and infrared from one side and RF from the other side. Now, white LED. Two technologies in white LEDs are used. Phosphor-based LEDs. This technique involves the use of blue LED coated with a phosphor layer that emits yellow light. So basically you are using yellow light for communication. The phosphor layer absorbs a portion of a short wavelength light emitted by the blue LED, and then the emitted light from the absorber experiences wavelength shift to a longer wavelength of yellow light. This kind of LEDs are used for visible light communication at the transmitter side. So the intensity of your light is modulated by a certain frequency, and you change it so frequent according to the incoming data bits that you want to send. So now this is one of the key differences from RF. In RF, you modulate the sinusoidal signal, the electromagnetic wave, sine and cosine. You can modulate them, the amplitude, phase, frequency. But here, mainly, you are modulating basically the intensity of the light, which is the intensity is kind of related to the power, and power is related to the amplitude. So, and you use this at the transmitter. And this LED there is a driver before the LED that changes this intensity of the light based on the incoming information. For example, you can do this using an on-off keying modulation schemes. If 0 comes, reduce the light. If one comes, increase the light, or even shut off the light, but the user will not feel that there is any flickering or any light discontinuity, because it's so fast, the switching is so fast that your eye cannot recognize it. And that's really, really amazing thing to have. And this is a response for the people who are saying that visible light communication is very sensitive to flickering. It doesn't get affected by flickering, because you switch your data and switch the intensity of your light very quickly, like let's say more than 1 million times a second, in order to transmit and communicate your data. So at the end of the day, it doesn't get affected. And the best thing about that is cheap. It's not that expensive. You can use it at home. You can just go to the market, buy it, and instead of using it for lighting only, you can also use it for communication if you are able to build the transmitter and receiver in a very proper manner. So the white LED, we have used, these are the white LED, phosphor-based LED, and the trichromatic LED generates white light by combining red color, which has wavelength of 625 nanometer, green 525 nanometer, and the blue 470 nanometer, and that's why we call it RGB, red, green, blue, in a correct proportion. So they have very high speed, enables very high speed switching speed, enables color control. You can control the color. And typically, these triplet devices consist of a single package with 3 emitters and combining optics. They are very attractive for visible light communication, as they offer the possibility of wavelength division multiplexing. You know, wavelength division multiplexing is one of the techniques that enables multiplexing different carriers, different wavelength. So instead of using one wavelength for communicating your data, you are using multiple wavelengths, and each wavelength is carrying and sending its own stream. So let's say, think of that like MIMO. Instead of using one antenna for communicating your data and getting 1 giga, you can use 10 antenna and get 10 giga. The same here, when you use more wavelengths, more frequent, you kind of increasing your data rate significantly. The most important factor in visible light is the switching properties of the visible LED. Yes, the switching capability of the LED should be very high. Yes, because you are using this for modulating your data. You are using it to modulate the intensity of the light according to the incoming data information. And this has to happen in a very fast manner, so that nobody can feel that the light is dimming. Yes, you are constantly changing the light level of your LED. But this has to be done to transfer your data while not allowing the user to recognize that there is any flickering or any dimming in the light. The light quality, the light intensity, the light, it's not recognizable by the user. They have the ability to be switched on and off very rapidly. This is what it means to have high switching capability for the LED, thereby making it possible to impress data on their radiated optical power intensity easily. Modulation speed of light of white LEDs is limited due to the relaxation time of the LED. This is one limiting factor in LEDs. Bandwidth of trichromatic LEDs is less than 20 MHz. Bandwidth of phosphor-based LEDs less than 5 MHz. So as you can see, the LEDs, they are different in terms of the bandwidth. The bandwidth of the LED can serve as the system bandwidth, yes? although, you know, although the spectrum is very huge and massive around visible light communication or invisible light communication region, but unfortunately, if your lid, you think of the lid like the beam width, the the bandwidth of your antenna, yes? So the bandwidth of your antenna, the higher it is, the better your system. You can use one antenna to operate over large bandwidth, different number of frequencies. And here the bandwidth of the lid is very critical, because the higher the bandwidth, the more capabilities it can give you in terms of utilizing the spectrum at visible light communication. Now, the bandwidth of the lid can serve as the system bandwidth of your whole system, and that's why there are differences in the cost between lids because of these features. It's exactly the same way in antennas. You have differences between them in terms of cost and quality because of the bandwidth they cover. For example, you can design an antenna to cover 2 megahertz bandwidth around certain frequency. Another researcher comes and design an antenna that can cover 10 megahertz around the same frequency by changing the geometry and playing with the physical parameters of the antenna. The same here. Whatever you have learned in the antenna design, you can come here, but you are here not in the electrical domain or the RF. You are in the optical domain. So basically, it's visible light communication, not electromagnetic waves, not RF signals anymore. And you can use these once you design them. You can propose them to be used with the visible light communication systems. So this photo shows an illustration of the visible light communication concept, and this is for the downlink only. And another link for the uplink is also needed to communicate between your users. So here, what do you have here? Let's see together. What do you have? You have a transmitter and a receiver. The transmitter is basically, you have your server. Let's say this is YouTube server or Facebook server that contains the videos, contains the pages, the groups, whatever. And you have the internet network and the applications on the server, whether they are websites or multimedia or augmented reality or real-time gaming, whatever. You get that based on the IP, the address, and many other things. You get your application, and through the internet network you transmit it until you reach to the access point. This access point is basically the light bulb, the lid. Now this is acting as a light bulb for illumination purposes and for conveying and sending your data bits as well. And this is, of course, it's powered. It has power over Ethernet or power line communication to drive this modem of your. There is a modem or a driver or optic chips just before the lamp that's responsible. There is kind of processing here responsible for modulating the light intensity and sending the information to the receiver. As you can see here, there is no antenna, there is no RF, there is no complex transmitter structure whatsoever. You only have lid and driver before the lid. And this driver modulates the intensity of the light, and then you send it to the receiver. At the receiver side, we only need photo detector. There is no antenna, no RF chain, no much complexity, no oscillators and these things. That's why the communication in visible light communication, we call it non-coherent. Non-coherent means I don't need the carrier frequency. I don't need to know the carrier frequency and synchronize to it and be very strict with it, because it's intensity modulation and using lid and photo detector at the receiver side. So this makes it really, really unique in that aspect. And then you have some amplifiers here that can optical amplifiers that can amplify your signal and process it and prepare it to be received by the laptop. Suppose you are transmitting a video here, you will receive video on your computer. How did you receive this video? You received it by using visible light communication, the light bulbs, which is amazing and very critical and very useful thing to have. Now, where is the other thing that we need to be careful about? The design, how to design this transmitter and design this receiver so that you can make it work properly. You have a electrical network extension of internet, passive optical network, wireless over power line communication system. So this basically shows you how to power your light bulb, how to drive your light bulb with the data and not interrupting the illumination functionality of the LED. So basically you have your PC power line modem, existing power line, and you have here kind of filter, band pass filter, and then the signal is biased, and then it goes to the LED directly and you transmit it. And at the receiver side you have photodiode, and then demodulation, and then at the mobile terminal, which can be your smartphone as well. So I'm talking, this is the driving circuit here. This is the driving circuit before the LED. And this is another block diagram that shows the visible light communication system where you have dimming control. This dimming control controls the intensity of your light, and you have a driving circuit, communication module to deal with the input data, LED array and optical lens. Optical lens like for focusing the light, and you transmit it over the channel. And the channel in optics is different than the channel in wireless. It's not very scattering in optics, yes? Optical concentrator at the receiver, optical fiber, and then photodetector, amplifier, output data and to your receiver, to your sink. Here you have different scenarios, indoor scenarios, for configuration for indoor optical links. You have the direct line of sight link, which is shown in this figure. You have the transmitter, receiver, and as you can see, the transmitter and receiver beams are aligning with each other. And this we call it line of sight connection. And we have the case when we don't have direct line of sight, we call it non-directed line of sight link. And this is the case where the light is not reaching directly in the line of sight link to the receiver, but it's getting reflected off the walls. And of course, the reflections are very little, and the receiver has to be extremely powerful and sensitive to get the data from the multipath reflections, because the signal to noise ratio in this case will be lower than this case. And you have the diffuse link in C, where you have line of sight and non-line of sight and multiple reflections, and you have quasi-diffuse link that's shown in D. So all these are different scenarios that you can experience in indoor communication using visible light. So since LEDs are used for the dual purpose of illumination and communication, it's necessary to define the luminance intensity and the transmitted optical power. Transmitted optical power indicates the total energy radiated from a certain LED. Luminance intensity is used for experiencing the brightness of a LED. Luminance intensity is the luminance flux per solid angle and is given as follows. You have the intensity is basically the luminance flux, which is this theta, over the spatial angle omega. This is the intensity. How much light going through certain angle. And theta can be calculated from the energy flux using this formula. This V of L is the standard luminance curve, and Km is the maximum visibility, which is around 683. And from these equations, if you know the angle, the spatial angle of your light beam, and you know the amount of energy crossing this spatial angle, you can know the intensity, because intensity at the end of the day, it's the amount of power over the region crossing that over the region that this signal is crossing through. In fulfilling the lighting requirements, a single high luminance efficiency LED can only provide limited luminance flux and over a limited area to illuminate a much larger environment, which means if you use one LED inside your room, you will have a coverage similar to this curve shown here. Yes, on the bottom left hand side. Which means that in the middle you have very high intensity, very good signal to noise ratio, but when you go away from the middle, go to the edge of the room, you will notice that you have very low signal to noise ratio. And the reason for that is the one LED cannot give high signal to noise ratio, high intensity level over all the over the whole region of the room. But if you want to increase the make sure that you have good high quality signal to noise ratio in all the spot lines inside your room, you need to use multiple LEDs simultaneously. And this is in order to illuminate a much larger environment. Spatially distributed LED clusters would be needed. Cluster of LEDs are connected with each other to provide high quality coverage. So inside your room, now you, instead of using one light source, you need to use at least 4 or 6 light sources, so that you can get very good high quality signal to noise ratio at any position in the room. And we call this LED array array of LEDs, and the luminance distribution for one transmitter and this, for example, shows the case when you have one LED, and here for 4 LEDs. The bottom right side of the figure here, you can see that the signal to noise ratio, the red color means that the signal to noise ratio or the power is high. So it's this region, the red region, is much more than the one here. In terms of area, the area of the red region here is larger than the area of red region when you use only one LED. And this some of you might say it might increase the cost, but I tell you, if you reduce, if we get LEDs that are cheaper than the current available lighting systems, then you can easily use them for for providing very high quality signals and getting light, and also for decoration you can use them with different lights. So an example of a visible light communication system with the system parameters: you have a room with size 5 by 5 by 3, the length, width and height. The source, you have 4 LEDs, they are positioned at these locations, and you have receive plane above the floor, active area 1 centimeter, half angle elevation and azimuth of the receiver, and these parameters are related to the transmitter. So here is the result. Optical power distribution in received optical plane for using 4 sources, and the angle, the full width angle is 70 20.5 and with reflection. So when you when you put in case A, this is case A, when you have the angle 70, you get very high signal to noise ratio on over most of the regions inside your room. When it is 12.5, what I mean 12.5, this is the spatial angle of your beam. Yes, the spatial angle of your beam. So when you make it narrower, you basically don't get very high good coverage over the whole room. And so in the middle between these slits, you will have low signal to noise ratio, and this low signal to noise ratio, you cannot receive the data in a very high quality, similar to the point where you have red here. And here, for the case when you have reflections from walls and 70, you get also very good high signal to noise ratio because you have reflections. Now, what about the channel model? Now, we talked about the transmitter and receiver, but we didn't talk about the channel model in optical communication. So the output power spectral density of a white phosphor baseplate solid line which corresponds to the left axis is compared to the measured spectral reflectance which corresponds to the right axis. So here the left axis is the power spectral density, and here you have a spectral reflectance on the right axis. And you have the wavelength here, and you have different material. You have the floor, the ceiling, the plastic wall, plaster wall, and different. And we are denoting them by different lines. So as you can see, the power spectral density coming due to floor is more than the one coming from ceiling. And the same with the reflectance. So this shows you that the material affects the reflectivity of your light and affect the characteristics of the power spectral density. And these two parameters have direct influence on the channel characteristics of your optical wireless signal. And therefore, you will end up having different characteristics for the channel based on the material inside your room. And also you can get multipath effect, which can limit the channel bandwidth. For example, for this case, where you have one lid and one receiver, you have one line of sight path and you have multipath effect coming reflected from the wall. Plus, you might get also multi-source interference. Yes, multi-source interference. Suppose you have two lids and the adjacent lid is operating on the same frequency as this lid operates, and if they are not far from each other enough distance, they might interfere with each other and cause interference, and this interference is the limiting factor to the signal to noise ratio and accordingly to your data. The impulse response of the channel is modeled as a short impulse caused by line of sight path followed by a broad pulse multipath. So basically, when you transmit your signal, the line of sight path gives you this pulse, and the reflected path gives you wider pulse with shorter amplitude, with smaller amplitude. And this region is coming from the multipath, and the first pulse is coming from direct path. So think of that as a two-tab channel. Yes, the first tab is the line of sight, and the second tab is the multipath. This is line of sight, this is non-line of sight. The delay between the two parts is determined by room geometry and size. Room geometry and size is the one that determines the delay between the two pulses. The non-line of sight part is usually modeled as a Gaussian pulse. You model it. And this is basically in most of the optical wireless channel, you get a channel similar to this behavior. So as you can see, it's not rich scattering channel. Yes, it's not rich scattering where you have Rayleigh fading, Nakagami fading, and all these things. And also it's not very dispersive. So the performance limits here, system is typically either bandwidth limited or background light limited if daylight falls on photodiode. Yes, because it's very sensitive to the other lighting sources around you, especially to the sunlight. And the bandwidth limitation is coming from the lid characteristics, yes? Because each lid has different bandwidth than the other. If channel bandwidth limited, use higher order modulation or equalizer. In case the channel bandwidth is limited and you cannot utilize it to send extra data bits, you can use higher order modulation or equalizers in order to send more data bits and increase the speed of your internet. If the background noise is limiting your communication, you can decrease the symbol noise, but if it is shot noise due to receive intensity, then you cannot do much about that. And sometimes the channel state information is needed at the transmitter to process the data in a proper manner. Signal processing, optical and electrical filtering. Block out of band background light. You can use electrical filters to block, or electrical or optical, to block out of band background light to reduce the interference. Remove electrical harmonics as well, because electrical harmonics cause interference as well, adjacent interference. And then sometimes also equalization is required. Bandwidth limited by LED response and by multipath. Types of equalizer, you have the FIR filter and linear mean square algorithm you need to use with that, decision feedback equalizer, mean least square equalizer as well, which are very complex. Last two are very complex. All these are in order to remove the interference and remove the effect of the channel in your signal. So the challenges and solution, as discussed before, main challenges for indoor VC are connectivity. While moving, users need to be connected when they move inside the indoor environment. Multi-user support in large areas is vital. Many users need to have access to the network at the same time. Dimming is an important feature in visible light communication when communication is integrated with lighting. Shadowing happens when the direct paths from user to all sources are blocked. All these are problems. All these are impairments, hindrances, and we need to deal with them. So what are the solutions for this? The solution for connectivity. While moving, yes, when you move, you might lose the connectivity. What's the solution? This problem is similar to the connectivity problem in cellular network when you move from one area, one base station, one city to another, while speaking with cell phone. The solution to this problem is called handover. Yes, this is the first base station, this is the second base station, and this is the mobile. Once the mobile gets out of the region related to the base station 1, you get connected with base station 2. And this is done via handover process where the two base stations talk with each other and send information about the user, and they mention to each other that this user is moving with this speed, is approaching this region, please move the data to the next base station and start serving this user from the next coming base station. The same you can apply to optical wireless communication. When the user moves out of the coverage of one LED, the LED can communicate with the adjacent LED via controller and move the data, hand over it to the other LED so that it can take care of the connection. Handover is done in the area that two base stations have common coverage. And similar solution can be used in signal processing domain for visible light communication. The user can be transferred from one light source to another in the area that's under the coverage of both. The handover process happens exactly when the user is in between the two base stations. This is where it happens. And so this was the solution for connectivity. If I ask you, well, what's the solution for connectivity in visible light communication, you tell me it's handover process, which is similar process used in cellular wireless systems. What about the multi-user support? If you have multiple users are being served with one LED, how do you do that? The solution is to use time division multiplexing. Divide the whole time into multiple time slots. And each frame is divided into equal time slot. Each user transmits data in one time slot in a predefined order. By doing so, you can serve multiple users simultaneously. Now you tell me, since you are dividing the time, the users won't experience any delay. They don't experience any delay because the switching, the switch used for interleaving and taking samples for all the users is very fast, faster than you can realize. And since the switching is very fast, you can serve multiple users within the same time by dividing the whole time into slots, and each slot is allocated to specific user. If you don't want to use time division multiplexing, you can use CDMA, code division multiplexing, where you assign a code for each user. So you assign a code for each user in CDMA. Each user transmits its data using the assigned signature pattern. It's used in 3G and 4G cellular networks, and it has been adopted and developed for optical systems as well. Optical orthogonal codes are used as signature pattern for users. So what's the solution for multi-user access? Then in this case, TDM and CDM. Last solution is spatial multiplexing. If you don't want to use TDMA and you don't want to use CDMA and you still want to serve multiple users, you can use spatial multiplexing. Spatial multiplexing, you can use it to increase data rate or to add users, rely on LED arrays and multiple receivers, or can use an imaging receiver camera. So here is the scenario where you can use spatial multiplexing to serve multiple users. So we have three solutions then: TDMA, CDMA, and spatial multiplexing to handle multiple user access to the access point or base station that's operating on optical region. Solution for dimming. Two main solution. Yes, this is a solution for the people who are saying dimming issue. What if I want to reduce the level of the light? How can I communicate? I mean, should I keep lighting the lamp with very high density or intensity? It's not very nice experience. Here the solution is basically two main solutions. The solution is using pulse width modulation for controlling with other modulation scheme in order to control the duty cycle of the transmitted signal. By controlling the width of the pulse width, the dimming level can be controlled. If you control the width of your signal, the dimming level can be controlled, reduce it, increase it based on the requirements. And the other solution is using pulse position modulation. Pulse position modulation, kind of a different technique, is alternative to pulse width modulation. that you use the position of the pulses to send and control your signaling instead of the width. In these schemes, multiple pulses are transmitted instead of one pulse. By controlling and changing the ratio between the number of pulses and the length, the dimming level can be altered. Now this is the solution for dimming. You use pulse width modulation or pulse position modulation. What about the solution for shadowing? Shadowing, as shown before, if you have shadowing, then you will not be able to receive the line of sight pulse coming from the transmitted signal. You will only see the multipath effect. So the impulse response has two parts. When the line of sight part, which is received via direct path, is blocked, the impulse response is only the second part. So you basically, your data in the second part in the multipath, then the data can be recovered using the second part, which is indeed the received data from the indirect path, the multipath signal. So in case of shadowing, then make sure that you have reflection. And from that reflection, you can get your signal back and demodulate it. Of course, it would be very challenging and much more difficult than the normal case. But you have to deal with it. At the end of the day, you don't want to lose communication. You have to be able to maintain your communication in spite of the fact that you cannot receive it from the main link. So that's why this is very problematic issue that you may face and encounter while you are using optical wireless communication, in case you don't have multipath reflection and you have shadowing where the main path is blocked and not received correctly. So these are the main problems. One quick review of all of them. Connectivity issue, you solve it with handover. Multi-user support, you solve it with time TDM, CDM, or spatial multiplexing. And you have the dimming issue, you solve it with pulse width modulation or pulse position modulation. And you have the shadowing issue, you solve it by designing the receiver in such a way it can get the data from multipath effect. So this is the part related to the problems and solutions. Now I want to continue with the part related to the modulation. So you have, this is the transmitter and receiver structure. And here we have line of sight, direct, non-direct line of sight, and you have the Wi-Fi, the differences between them. But I want to talk about the modulation, the digital modulation in optical communication system. This is very, very important, critical point that I want to draw your attention to. So having understood the benefits, advantages, challenges, and solutions of visible light communication and how to use the light for communication, now what are the key differences to RF? Yes, in terms of modulation. And now go to think like engineers. The first presentation was like for kind of giving you an overview about visible light communication and LiFi technology. But now let's think as engineers. Having understood the properties of optical wireless communication and how it works, now how can we design efficient modulation schemes for optical wireless communication? In RF, compared to RF, we have been designing systems for RF where the information is carried on electrical signals, and therefore the signal in RF domain can be complex. What does it mean to have a complex signal? Can you tell me? It means that it has when you have an RF signal, means that you have sine and cosine, two orthogonal, two perpendicular orthogonal carrier that can carry two streams of data. And the signal in RF can be bipolar, which means that the signal can be positive and negative together. But when you go to the optical communication, in optical communication you are using optics, you are not using RF, you are not using antenna, you are using LED. So the LED cannot like allow the transmission of kind of sinusoidal signal, sine and cosine together. We don't have such thing. That's why you cannot use complex value. You only use real valued signals, which means only one direct intensity modulation link. Plus, you don't have unipolar. You don't have bipolar. You have unipolar communication. You don't allow non-negative. You don't allow negative area. It's all positive. So then these are the two key differences from RF. Your modulation should be real valued, no complex value, and unipolar, non-negative. So now how can you then modify the current modulation schemes and make them applicable for optical communication? That's very critical thing. For example, if you are going to use this is the transceiver structure. You have the transmitter, the bits coming, and you have the modulation encoding, pre-distortion, digital to analog conversion, pulse shaping, DC biasing, LED non-linearity, and then you have the optical wireless channel. The LED here, the modulation here, you are not allowed to transmit complex values and not allowed to transmit negative values. But how do you do that with modulation? This is what we are going to learn. So here, one solution can be to use a single carrier on-off keying. Based on the incoming data, you turn the light on and off, on and off, and on and off in a very fast switching manner. Or you use multi-level. Here you have two levels, binary, on-off keying, or you can use multi-levels. Of course, when you increase the number of levels, you increase the spectral efficiency and you can send more data. What about OFDM? Can you use OFDM with optics? Yes, you can use it if you make some modifications. So the modification you are using here is the pre-distortion here. You are using mapping the symbol, clipping, and zero. You want to make sure that you are not using negative signals and not using complex. So if you use a QAM, one of the solutions is to use DC offset OFDM. Basically, the signal after taking the IFFT, the signal can have positive and negative value, the amplitude. So what do? You bias it using a DC value to make sure that the signal is positive. So now you solve the problem of the negativity, of having negative signal values. But what about by using DC bias? But what about complex values? How to overcome that? You have another one, you multiply it by another one, you take the QAM conjugate, so that the QAM symbol, when it gets multiplied by the QAM conjugate, you get real value. Because any complex number you multiply it by its conjugate, you get a real number. You don't get an imaginary part anymore. And that's one of the tricky solutions for the modulation of OFDM. And this is the time domain signal, the part related to it. And here the signal, the time domain signal of OFDM, the OFDM generation, here you have the signal in time domain. These are the samples related to the CB, and these are the samples related to the main OFDM symbol. After you take the IFFT and see the distribution of the samples, you will find out that the distribution of the sample has Gaussian distribution. Gaussian distribution Gaussian distribution in this case is very difficult thing to have, very bad characteristic that you end up seeing sometimes in your system, and this is not recommended. Why is that? Because when you have Gaussian distribution, the peak to average power ratio will be extremely very high, and therefore you will have high peak to average power ratio that can affect the signal fluctuations, and based on that, power amplifier characteristics will affect your transmitted signal, and it might cause some clipping to your signal and lose some part of your data, which is not nice thing to have, and therefore you need to make some modification ahead of the time to your transmitted signal so that you don't get this distribution in time domain. You get a different distribution close to the uniform signals. So this is the clipping that can happen due to the power amplifier in case you are not operating on the recommended area. So I just want to remind you of before we finish this lecture, I just want to remind you of the main two important features of visible light communication when you consider modulation. The first one is complex valued. You don't have complex valued, it's real. And the second one, you don't have bipolar, you have unipolar. And basically, the simulation of these systems, how do you simulate these systems? The simulation of these systems, you just start from any OFDM code that you have for normal wireless communication system. All what you need to do is to make sure that your OFDM signal, for example, is real, the values are real, and it's positive. And how do you do that? By the methods I have just explained, by complex multiplying, by complex conjugate, and by using DC biasing or some other alternative techniques. For example, you can come up with your own method, your own technique. But also you can use on-off keying, pulse width modulation, or single carrier, or the signal, the modulation schemes that can directly modify your intensity. Now, where is the changes? The changes in the channel model. Now, since you are using optical wireless channel, the characteristics are completely different than the signal used for wireless medium. Therefore, now in the standard related to Wi-Fi, which is 802.15.7, you have a section related to the channel model, how to generate its parameters. And I tell you, it's even much easier than the channel parameters of the wireless signal. But you need to take that channel, generate the parameters of it, and replace your wireless channel that you have in your OFDM code with the signal, with the new channel model for optical communication systems. And then you have a complete optical simulation system, wireless optical communication system. As you can see, it's not much, no much differences. The only differences is these two things to consider while you are modulating your signal, and change the channel. And then you have a simulation set up for optical wireless systems. And in next coming lecture, hopefully we can share with you some codes on how to modulate and simulate optical wireless communication system. So with this, we can stop here and continue next time with the simulation part related to optical wireless communication, and talk about some of the other applications and some of the implications. But before we close here, I just would like to recommend everybody to go and check that this Wi-Fi topic and visible light communication is not something that's not implemented or theory. It's something that has been standardized and already used in the market. There are smartphones that can use visible light communication chips and communicate via light. There are access point and visible light communications system that can provide you data from the light. Plus, I recommend everybody maybe to go and check the Pure LiFi. There is a company called the Pure LiFi that's generating and producing a transceiver structure, transmitter and receiver, that use optical wireless characteristics to provide you with wireless access to the internet. And this company is a UK company, and they have hundreds of customers around the world. They serve them with optical wireless systems. But before we close, before we finish this lecture, let me explain one thing. Now, we explained that visible light communication is good and it has very good features. It can provide you with high data speed internet. But our talk was mainly concentrated on downlink, yes? What about uplink? Assume you are receiving your data from an access point, which is LED in this case, light bulb, but you want to also communicate with the base station via an uplink link. Do you still use the visible light region for uplink? Is it feasible to do it? I mean, whenever I want to communicate with my base station, with my LED, I have to transmit light. It's not really convenient to do so. That's why for the uplink transmission in visible light communication, they used infrared communication. Yes, infrared communication, it's not like light, and also you avoid the interference coming from the visible light region. And this is very convenient, nice solution to have for this. Now, what are the other problems that appear in the literature? The people who say that visible light communication cannot work in non-line of sight. No, it can work in non-line of sight environments, especially if the environment is reflected and the receiver is designed in such a way it can capture the reflected signals. The other point is the interference coming from the sun. Of course, the interference coming from the sun affects significantly, but you can use filters, optical filters, to minimize this interference coming from the sun. And therefore, you don't need to use visible light communication outdoor. You can use it only indoor and in the places where you don't have much interference from the sunlight. And for the dimming issue, the people who are saying dimming issue, and if you want to communicate, you always need to light up your lamp or LED. This is not true. This is not absolutely true, because you can reduce the light level to very significant amount that you cannot recognize there is a light while you still have your communication going on. And this is a response for the people who says that you always need to experience the light in order to send your data. And there is no flickering. You don't experience any flickering issues because the switching capabilities of the optical switch is so fast that your eye cannot recognize it and you cannot feel it. Plus, for the mobility issue, we said that you have the handover thing, and the handover process is already implemented in cellular system, and you can just deploy it again in LiFi networks. The last point that I want to mention is about the last point related to that is related to the interference when you have two access points next to each other and adjacent to each other. In this case, if the user is exactly located between these two access points, you might get severe interference. To avoid that, there is a solution called you have a unit, software-defined radio unit, responsible for assigning and managing the resources for the different LEDs. For example, you can have a scheduler This scheduler is responsible for assigning the bandwidth, the frequency, the resources for the adjacent access point so that they don't interfere with each other. And this is really a very viable solution. So, longest story short, visible light communication is really one of the technologies that has been already implemented and used in the market. Very powerful technology, and it's the future. Because it uses the light for two purposes simultaneously, for communication and illumination, and this is very nice thing to have. And most of the challenges associated with this technology have been almost resolved, and there are practical companies, really practical, already in the market providing you with these chips. If you want to buy smartphones with visible light chips, you can buy. If you want to buy access points, LEDs that can provide Wi-Fi connection, you can buy. But unfortunately, they are not very famous and available in the market. So thank you very much. And with this, we conclude our lecture. We can stop here and meet you in the next time. Thank you very Hi and welcome everybody to the lecture titled Error Control Coding. In today's lecture, we will be talking about channel coding mainly and the purpose of using it and its importance. So basically, it's gonna be a very important lecture that I want you to give too much attention to it, because it's one of the most important concepts that we usually deal with in wireless communication and in communication in general, and even storage. So the outline of the topic, we will be discussing several topics related to error control coding, and it's kind of a subclass, sub-course within the main course of communication. So mainly we will be talking and discussing about the concepts, the linear algebra behind error control coding, linear block codes, and cyclic codes and PCH codes, and the differences from RS codes, convolutional codes with RIP decoding, trellis decoding, turbo codes, and LDBC codes. So it's going to be very comprehensive topic, but mainly in this lecture and next one we will be covering the basics of error control coding. So what's error control coding in communication and storage? So we already discussed in the previous lectures related to communication systems that when you transmit your data over a channel, the channel in most of the cases is noisy, and since it's noisy, you are not sure whether you will receive your data bits correctly without any errors, or sometimes you will have some errors in them. So the point here, how do you detect these errors and correct them, because at the end of the day you need your transmission to be reliable from the transmitter to the receiver, and you want to make sure that this transmission is being held with less number of errors, with minimal number of errors. Error control coding, this new subject, is responsible for the control of errors so that efficient and reliable data transmission and storage is possible. So in 1948, Shannon, who's a scientist, was working on information theory and communication and the math behind communication systems, showed to the world by one of his paper that by the use of proper encoding of the information, errors introduced in a noisy transmission channel or storage medium, when you store your data on a disk, on a floppy, on a hard disk, hard drive, on a cloud, wherever, the information can be, the error in the information can be reduced to any desired level without sacrificing the rate of information transmission or storage, as long as the information rate is less than the channel capacity. This was the conclusion in a study conducted by Shannon in 1948, that you can design encoding schemes that can reduce the errors that occurred due to noisy channel to a very low level without reducing the rate of transmission, as long as the rate of your transmission is below the channel capacity. So this was the theory. The theory is saying you can design these codes in such a way that you avoid the effect of the channel, especially the noise. But how to design them? This is the question. How to design them, this is the responsibility of researchers, engineers, scientists to come up with practical design for encoding schemes that can avoid the errors caused by the channel. Now let's have a look at the most basic block diagram that we usually use for error control coding. You have your message, which is composed of data bits, zeros and ones, ones and zeros. And you have after that source encoder. The responsibility of source encoder is to compress your data bits and make sure they are not redundant, and in order to reduce the size of your data, and therefore you use less memory. And after source encoder, you use channel encoder. Channel encoder adds redundant bits to your message data, and these redundant bits, we call them the parity bits, and they are responsible for protecting your data from the noisy channel, so that you can receive all your data bits successfully and conduct your transmission in a reliable manner. After the channel encoder, you have modulator. The modulator, which are the topics that we have been discussed so far in the lecture, whether usually digital modulator like QAM modulation, PSK, FSK, binary phase shift keying, so on and so forth, or any other modulators. And then you transmit over the channel, and there is noise added to the channel, and then at the receiver side you need to use demodulator, then channel decoder, and then source decoder, which is after that the message estimate. You estimate your message, which is supposed to be equal to the transmitted message. So in today's topic, we will be talking and discussing and explaining and dealing with this block called channel encoder. So here you have the source output. The source output here, the output of the block called source encoder, is U. And this U is a vector of zeros and ones. Vector. Let's say 100 bits in it. And this we call it the information sequence. The encoder output, the channel encoder output, which is denoted by V, is called the code sequence. and the demodulator output sequence block R at the demodulator, you modulate it, you transmit it over the channel, and then you demodulate and you receive R. R is called the received sequence. So we have the information sequence U, the code sequence V, and the received sequence R. After the channel encoder, I must be able to get U, which is estimate U hat, which is an estimate of the information sequence. Yes? Ideally, U hat is a replica of U, although the noise may cause some decoding errors. Yes? U hat is basically what you transmitted at the transmitter. It's U. But since you have some noise and estimation errors and due to some other functionalities, U hat and U sometimes they are not exactly the same, and that's why we plot the bit error rate or some diagrams or curves that shows us the difference between the transmitted sequence and the received one. So here is the block diagram. Again, in most coded system, U, V, and U hat are binary sequences. They are zeros and ones. If the demodulator makes hard decision, R is also binary. R is binary. Hard decision, I mean the demodulator just decides yes or no. Is the bit above 0 or below 0? If it is above 0, means it's 1. Below 0, minus 1. That's why we call it hard decision. A good code is designed to minimize the probability of decoding error. Yes, the code that we want to design is a code that can minimize the probability of error. How do you calculate the probability of error? It's the probability that the received information sequence you had is not equal to the transmitted information sequence U. So basically you try to find what's that probability. So noisy channels, let's give you some examples on noisy channels. Where do we see these noisy channels? In phone lines, yeah? Transmission channels like phone lines, mobile cellular telephony, high frequency HF radio, microwave and satellite links. Satellite links, for example, your TV, the dish on your home receiving signal from the satellite. The main source of errors is due to noise. Optical fiber cables as well. And the noise disturbances can be due to thermal noise, crosstalk, switching impulse noise, and these are the main noise disturbances in the channel. Now, this is regarding the transmission. Yes, this is the noise affecting your transmitted data. But what about when you store your data in a storage? When you store your data in a storage, like core and semiconductor memories, magnetic tabs, drums and disk, compact disk, optical memory units, cloud, hard disk, SDD, SDV, whatever, those also are affected by noise. And this noise, the disturbance here is surface defects or dust particles. And both are the goal here, although transmission systems are related to communication science and storage media is mostly related to computer science, but both of these are basically trying to use error control coding in order to reduce the amount of mismatch between the transmitted information sequence and received information sequence. This is a simplified version of the previous block diagram where we have just digital source and U is the information sequence. After the encoder we have the code sequence. Then you have the channel you have R, the received sequence, and then decoder, and then the digital sync. So the main engineering problem here is to design and implement the channel encoder decoder pair. The main problem here, or your goal as an engineer, is to design the encoder and decoder pair, we call them pair, in such a way that the information can be transmitted in a noisy environment as fast as possible. The message can be reliably reproduced at the output of the channel decoder. Here, U hat is very close to U. And third, the cost of implementing the encoder and decoder falls within acceptable limits. What does this mean? This means that you don't increase the complexity. The complexity of your decoder is low. Why don't we like complex decoder? Because complex encoder and decoders, they cost us money in terms of delay and power and the processing. And in the future, we are mostly going to be using Internet of Things devices, which are limited in memory, limited in size, limited in power, limited in processing capabilities. So we want to reduce the complexity of this encoder and decoder as much as we can, so that we don't increase the overall cost of the system. Because if you increase the overall cost of the system, your system will become very expensive to a level that nobody can afford buying it. Customers, companies will not be able to sell it to people, and people will not be interested in buying it because it's very costly and expensive. So as an engineer, yes, you need to design something that's workable, that can achieve the goal and task of transmitting your data in a reliable manner, but also without increasing the cost to an unbearable level. Yes? So this is what we are aiming to achieve basically when we design the codes. What are the types of codes? Depending on the encoding structure, error correcting codes can be categorized into the following two classes. Block codes or convolutional codes. Block codes, they work and operate on block by block, while convolutional codes, they work and operate on bit by bit. Yes, it's sequential operation on bit by bit. You take the first bit, operate on it, get the output, then the next bit, next bit, next bit, and so on. While block coding takes block of bits, like let's say vector of 10 bits, 20 bits, and they try to, from this block of 20 bits, which we call the information sequence, we get a corresponding coding, a corresponding code word sequence that represents this information. But this code word sequence has some redundant bits in it. We call them parity bits that we can use in order to reduce the amount of errors and detect the errors, and if we detect them, try to correct them so that we make sure we receive our data reliably without any errors caused by the channel. So for the block codes, the encoder of the block codes operates on k information symbols at a time. On k information symbols at a time together takes them. A message block is represented by a binary k tuple. For example, you have your U, which is U0, U1, UK-1. U is vector and U0, U1 can be 0 or 1. The encoder transforms each message U independently into an tuple V. After the encoding process, you get V. Now V is also binary sequence, zeros and ones, but the length of V is greater than U, and it's like usually N, the value N is greater than or equal K. There are, now if you have, let's say, K number of digits for your message, Then there are 2 to power k different possible code words corresponding to 2 to power k different possible messages. Yes? If you represent this, your message by binary, 8 binary digits. Yes? Then how many different possible messages you can get? How many different possible messages you can get? You can get 2 to power k, whatever k is. Now we call the ratio of k over n the code rate, and we denote it by r capital equal k over n, and we call it the code rate, and this is usually less than 1. Why it's less than 1? Because n is usually greater than k. The number of bits after the encoding is more than the number of bits before encoding. For a binary code, in order to have a different code word assigned to each message, we have k, the k number of bits in the information sequence is less than the number of bits in the encoded sequence, and therefore r is usually less than or equal 1. If r is equal 1, this means that the length of the encoded sequence is the same as the length of the message itself, and we call that the information rate is the same for the message and the encoded sequence. They are the same. Now let's put this in action and go and take example. You have your messages here. Suppose your message block is composed of 4 digits. The message sequence length is 4 bits. Then how many different possible messages you might get? 16, because 2 to power 4 is 16. And you start from 0000 to 1111. And after, this is you. This is the message is you. After you encode it using the block encoder, you get a code word of length 7 bits. Now, as you can see here, the message itself, you put it at the beginning, at the end of the code, and then you put some other bits, like this message. Let me open the marker so that you can see it more easily. Now with the marker you can notice it, hopefully. So you have your message bits. Here is the marker. This is the message, and this is, we call it you. You put this at the end of the code word here, it's the message you, and then you put here some other bits. This is V, this is V, this is U. So when the message content is shown in the code word clearly, we call the encoder systematic encoder. When the message signal is not shown in the code word, we call it unsystematic. We usually prefer to use systematic because it's easier to deal with and it's much more desirable at the receiver side, especially in the decoding phase. Now let's go to the next message. It's 0001. You put it here, 0001, and you have some other bits here you add. How do you get these bits? You get these bits based on a generator matrix. This generator matrix, it works like a transform, and this transform is dependent on some basis function, independent vectors, and the data. Based on the data values, based on the message bits, you get these values. The message bits get multiplied by the generator functions. Let's say you have four basis functions like this, and the length of these basis function, and you have your vector here, message. Your message gets multiplied by the vector, and the result is 1 bit. By the next, and the result is 1 bit. These bits, you put them at the end of the message. We will talk about them in detail, but for now, let's just understand that the systematic encoder puts the message bits themselves in the code word. And the other bits, we call them these bits, 3, 3, 3 here. Because here, for example, the message, this one is basically this one, exactly. And the other bits, those one, we call them parity bits. Those are, why do we add these bits, and how do we obtain them? Using generator matrix, like a transform matrix that depends on the input and independent basis function. And what are these bits? Parity. Why? How do we use them? We use them to detect if there are errors on the message signal. This is how the block code basically works. Now let's move on. The code parameters are k equal 4 and n equal 7. In the k is related to the message sequence, and n is related to the code word length. N is equal 7. Therefore, there are a total of 2 to the power 4 equals 16 possible messages and code words chosen out of 2 to the power 7. Here is the thing. Here we have 16 messages, yes? But because 2 to the power 4 is equal to 16. But when we map 4 to 7 bits, in 7 bits, how many different messages we get? We get 2 to the power 7, which is equal to 128. True? 128 bits, 128 different possible code words. This is what you will get from the 16. But from these 128, we only select 16 of them to represent the 16 messages here. At the receiver, when you transmit them to the receiver, how would you know which 16 code words you have used? Due to this process, the receiver can make some mistakes in deciding on the code words, and therefore we need to limit the decision to only certain set. And this is what we usually consider at the receiver, and this will be evident and very clear for us when we explain this in more details in the coming slides and give you some examples. But keep this point in mind, that code words have larger number of possibilities, while a message less, and this larger number of possibilities, you only need to select a few of them, and the remaining, they cause kind of randomness. And this is not desirable at the receiver side, especially in the detection process. So that was about block codes. What about convolutional codes? The encoder for the convolutional codes operates on k information symbols at a time. A message block is represented by a binary k tuple. U is given as follows. The encoder transforms each message U into an n tuple. V is given as follows, which is the output of the encoder. The encoder is said to have a memory order of M if each encoded block depends not only on the corresponding message block but also on M previous message blocks. What does this mean? This means that for each input bit from the message, you produce certain number of output bits. These output bits, each one of them is dependent not only on the current value, but also on some previous bit values. And therefore we call this memory encoder. It has memory. Memory means it stores some values in the encoder because the output bit will be dependent on them later on. The ratio R is K over N, is called the code rate, similar to the block code type. So there is no much difference here, but here it operates on bit by bit and you have memory. Give you an example of a structure. So the structure looks like this. You have U, you have U, you have V, you have delay element. The delay element are the ones in the square here, and the exclusive OR gate is given at the output of each bit. So consider the information sequence U equal 10110011 with the leftmost bit assumed to arrive at the encoder first. This means that this bit enters the encoder before the other bits. So basically you have 11001101 entering to the encoder, and this is U. You are required to determine V. So at each time unit, K equal 1 information symbols enter the encoder. Only one bit enters the encoder. And N, the number of output bits, is 2. 2 code symbols are produced. The code rate, symbols here represents bits because we are using bits. The code rate is R equal K over N. Now question, if for each input bit we are producing 2 output bits, what's the code rate in this case? The code rate R is equal to K over N. True? K is the input bit 1 and N is the output bits 2. So K over N is half, 1 over 2. The encoded code sequence is therefore given as follows. Now, how do you obtain this? For example, for when 1 enters, you get this value 10. The next bit you get 11. Next you get the. How do you obtain this? How do you obtain this? Let's see. I said the value here, you have V here, yes? V is vector, and this vector is producing 2 bits. Let's call them V1 and V2. V1 and V2. This is coming from V1 and this coming from V2. And this is a switch, kind of taking this value, then this value, this value, then this value. True? And let's assume this sequence of bits is entering the encoder here. Yes, it's entering the encoder here, and we want to find the encoded bit V. So what will you do? What will you do? Tell me. You will take this bit 1 and push it to the encoder. So you have 1 here. What do you have here? 0. What do you have here initially? 0. Then the output V1, what would be the value at V1? V1 is equal to this, the value, the bit here from this branch, the bit from this branch, you take it, and the bit from this branch, you take it, and XOR them, exclusive OR gate. 1 XOR 0 is equal to 1. Yes, 1. Again for V2, so V1 is equal to 1. For V2, how do you find V2? You take the bit at this position, and the bit at this position, and the bit at this position. As you can see, there are 3 arrows. So for V2, you come here, it's 1 XOR 0 XOR 0, and it's equal to 0, 1 with 0, 1, and 1 with 0 XOR 0 equal 1. Then the output V2 is also equal 1. So for when the input bit is 1, the first bit is 1, the output will be 1, 1. So here, this is 1, and the output here in V, 1, 1. Now, let's say that 0 after 1 comes here. After 1, there is 0. So what do? You erase this 1 and move it here. 1 now is here after the delay. Yes, you put it here, and there is a new 0 comes into the circuit here. The 0 is here. So now you need to determine what's the value of V1 and V2 again. How do you determine V1? V1, you take the bit at this position and the bit at this position. The bit at this position 0 and the bit at this position 0. 0 XOR 0, 0 XOR 0 is equal to 0. 1 with, to remind you of this is XOR operation. Yes? So here you have 0 here and 0 here, you get 0. So V1 here is 0. Now what about the other branch, V2? You have 0 with 1 gives you 1, the result of this, and 1 with 0 gives you 1. So V2 here, this is V2 1, I found it 1, and V1 is 0. This is V1. Let's take, so we finished the first bit 1, we finished 0. Let's take now the third bit 1. What will happen to the circuit? It will push these zeros one step to the right, because new bit is coming to the circuit, and we need to recalculate the value of V1 and V2 accordingly. So what will we get here? This 1 will move here to this, it becomes here 1, and this 0 will move here, so this becomes 0, and this is 1, 0, and then here the bit that's coming to the circuit is 1. So you remove this 0 and put instead of it 1. Okay? Now calculate V1 and V2. V1, you take the bit here at this position and the bit at this position. There are 2 arrows, and you XOR them. Here I have 1 and here I have 1. 1 XOR 1, 0. That's why I get here, this is V1 equal 0, and here 0. Now let's see the other V2. What's the value of V2? V2, you have 3 branches. 1 XOR with 0, 1, true, and 1 XOR with 1, here 1, XOR with 1, 0. That's why you get here also 0. V2 is equal to 0. Now new bit comes in, you need to shift this to the left again, to the right again. So here this one comes here to the 0, you remove this and put 1, and this 0 comes here, you remove 1 and put 0, and there is a new one coming here, this you removed it, new one is coming, new one, and you recalculate V1 and V2 according to the incoming information bits, and then you write this bit. So in the test or quiz or exam or whatever, if I give you a circuit like this, circuit, whatever, I can change this circuit a little bit, maybe increase the number of blocks. These we call them memory blocks, they cause delay. I can increase them or use only one and add more branches, remove some of the branches. At the end, I want you, if I give you an information sequence U, and this information sequence contains binary bit zeros and ones, and tell you encode this information sequence to a code word V that can represent my message in order to protect my data, to add some parity bits that can protect my data from the noise channel. By doing so, you can be able to find V that you need to transmit instead of U. So here you don't transmit U, the message signal directly, instead you are transmitting V. Clear? I hope this is clear because it's very important question, very important point. This is how convolutional codes work. Now let's move on. Types of errors. There are two types of errors mainly. In memoryless channels, what do we mean by memoryless? There is memory and memoryless. Memoryless means the output bit, the output in the channel, does not depend on the previous values. It just depends on the current values. So in memoryless channels, transmission errors are random in the received sequence, and memoryless channels are called random error channels because they are memoryless. This means that if you have a sequence, received sequence like this, then the channel affecting each one of these bits is independent between these bits from one bit to another. They are independent from each other. In channels with memory, noise, this is in memoryless, the noise is independent from one bit to another. But in memory channel means that the output value depends on the current and the previous ones, like convolutional codes. Noise is not independent from transmission to transmission, is not independent from one bit to another. There is kind of correlation between them. Why? Because it's memory, it has memory. There is dependency on the previous bits. And the channel can stay in a bad state. For example, the channel can remain in bad situation for consecutive uses of the channel. For many different bits, the channel can remain bad. These channels are called burst error channels. You don't have one single error, you have consecutive number of errors located in one in certain sequence, and this we don't like it. It causes severe degradation and severe reduction in the bit error rate, severe number of bits. It increases the error in the system, reduces the reliability, and we need to come up with techniques or special coding methods that can overcome this. Okay, these are the different types of errors we have, and then what are the error control coding strategies we use? We use one-way communication systems, and one-way communication system means there is no retransmission. You just send once. your data, and for this we use forward error correction. There is no communication or feedback between the receiver link, the uplink, the receiver and transmitter, and this relies on automatic error correction. First you detect and correct, detect and correct, detect and correct the bits. While if you have two-way communication systems, we use automatic repeat request, which relies in error detection and then try to superimpose the packets and enhance their reliabilities. Let me give you example. Which one is better? Here I have a transmitter and here I have receiver. Which one is better, to use forward error correction or ARQ? This is one-way communication system, this is two-way communication system. You tell me, it depends on the requirements of the system. If if your system or your application does not tolerate delay, does not tolerate like being having any delay on your communication, like you are making real-time communication, real-time voice call, real-time video, sometimes something that's very sensitive to delay, then it's better to use forward error correction, because forward error correction just encodes the data and sends it once. However, if you can tolerate delay, some delay in your system, you can allow it, then you can use ARQ, automatic repeat request. How does this work? Your packet, you basically transmit your first packet to the receiver. The receiver tries to decode the packet, receives the packet, tries to decode it. If the receiver finds some errors in the packet and he was not able to decode the packet successfully, then he declares error. There is error in the packet. Since there is error, he cannot go and use it for decoding the application or using it later on the upper layers. He asks the transmitter to retransmit the packet again one more time because the first packet was in error. So to do that, the receiver sends a NAC message. NAC message means I didn't receive the packet correctly. ACK message means acknowledgement, I received the packet correctly, and don't transmit the packet again, transmit a new packet for me. Based on this, you can keep retransmitting your data until you receive it successfully, or the maximum number of allowed retransmission are expired, are already used. So now let me ask you this question. Suppose you have two applications. One is FTP or web FTP application, file transfer protocol application, or web browsing, or mail like Bob mail or SMTP mail. Let's say mail. For these applications, which one of these coding is more suitable? ARQ or FEC, forward error correction? I think you already know the answer. ARQ is more suitable. Why? Because these applications, they do not tolerate any errors. They don't accept any errors. If there is a single mistake, a single error in the file you are uploading to the server or to the website, the file will not be accepted and it will ask you to re-upload the file. Yes? This is very critical to understand. What about web browsing? When you ask for a web page, if the web page cannot be displayed as whole correctly, it will not show you the page because it's very critical. What about mail? If you send a mail or message, do you tolerate any errors? You don't accept any errors. You tolerate delay, but you don't accept errors. That's why for these applications, mail, web, FTP, you use ARQ because you don't care too much about delay. You care a little bit more on the quality, the reliability of your connection. Now, on the other hand, let's say you are using voice communication, voice or VoIP, voice over IP, or real-time gaming or video. Which one of these coding techniques you will use? Forward error correction or ARQ? Forward error correction. Why you will use forward error correction? Because these applications are very sensitive to delay. It cannot wait for the receiver to decode the packet and then send an ACK or ACK to the transmitter and wait another time to transmit the packet one more time and then combine it and decode it. It causes delay, and voice and video, they cannot afford delay. So you give up on the performance, on the reliability a little bit for the sake of obtaining real-time communication with no delay. Okay, I hope you understood these now, the differences between them, how they work, forward error correction, ARQ, which applications use them, and what are the differences between them. Now, error control coding strategy. Forward error correction achieves the constant rate of information transmission and does not require a feedback channel. This is the most critical point. Does not require a feedback channel. Okay? There is no feedback channel. On the other hand, high reliability requires complex decoder. These usually use complex decoder, unfortunately. Okay? On the high required ARQ achieves high reliability with simple decoders, but requires feedback channel and achieves variable throughput and increases the delay. Okay, these are the two key differences between them and that we should be careful about. So now you have basic knowledge about error correcting codes, the differences between the memory channel and memoryless channel, the differences between convolutional codes and the block codes, the differences between forward error correction and ARQ, and what are the features of each one of them, and also, not only this, but also for the applications that are using each one of them. So with this, you have some basic understanding and basic knowledge related to error control coding. We can stop here and continue in the next part that will come soon after this lecture, maybe after a few hours or few. Thank you very much and see you in the next part.